All right. This week we're going to be talking about sound. Last week we talked about waves. And so this week we're really going to kind of try to apply these ideas of waves to sound. All right. Remember, red slides, write things down. You should have your sound handout. Don't forget to look for the owl and tell me where he is. And make sure you give me your little 2 or 3 sentence summary at the end. Okay, so sound energy is caused by an object's vibrations, and sound energy is kind of both kinetic and potential energy together. But really, what I want you to think of when you look at this is what's going on with all these little dots here. And so we have a speaker on the left-hand side here, and if we could see the air molecules, which we can't really see air molecules because they're too tiny, plus they're invisible, so we can't really see them. But if we could see the air around us, this is what it would kind of look like. Whenever there's a sound, all the sounds around us would make the air do what you're seeing right here. It kind of squishes them in a little wave-like pattern. And the waves are kind of, the particles are basically bumping into each other and passing that along, just like the Newton's cradle that we've seen in class a lot and things like that. So this is really what sound would look like if you could actually see the air molecules. Now, I want you to watch this little video clip that I have up here, and this is a really old video clip, but I think it does a good job of showing you what sound is.
We can record pressure variations in sound waves with this kind of instrument, an oscillograph. Sound waves are striking the diaphragm at the left. The stylus records the sound waves as a graph. Later we shall use such graphs to represent sound waves. Condensations cause the stylus to move upward. Rarefactions cause it to move downward. So far, we've seen how sound waves are produced. Next, we'll identify 3 auditory effects of musical sounds: loudness, pitch, and quality. We begin with loudness. Every sound sets up a disturbance in the transmitting medium. The larger the disturbance or displacement of the individual particles, the greater is the height of its graph above the neutral line. This displacement above the neutral line is called amplitude, and it is amplitude that determines loudness. As its loudness increases. Next, let us consider pitch, the auditory effect of frequency. First, we hear the sound of middle C. Next, we hear G below middle C. And now the sound of C below middle C. What causes such differences in pitch? To explain such differences, we picture 2 different sound waves. Here, the lower fork makes more complete vibrations per second. Therefore, its frequency is greater. It is evident that the one with the greater frequency has the higher pitch.
So one thing that we need to do here is we need to take the things that we know about waves, and specifically wave properties. And remember, wave properties include amplitude, frequency, and wavelength. And you should really have a good idea of what those things are at this point. So we need to take those ideas and talk about how does changing those different types of properties, how does that affect the sound we hear? So what I want you to think of when you're doing this is that we have wave properties on one side and that we have sounds on another side. And when we change the wave properties, like if we make the amplitude bigger or smaller, we should understand how that affects the sound that we hear. Okay, so starting with amplitude. Now, I want you guys to draw these little waves here and be really specific about how you draw them. So notice that this wave here is shorter. It has a smaller amplitude, and this wave has a nice big amplitude. So in your notes, make sure that that's very clear. Those two waves should not look exactly the same. One should be really short, and the other one should be really tall, and that's the only thing I want you to change about it. Don't stretch them out this way. Only stretch them out this way. Just make it taller. Okay? So, one short wave, one long wave. So when the amplitude is small, we get a quiet sound. And when the amplitude is big, we get a loud sound. All right? So amplitude affects the volume of the sound. Small amplitude, small volume. Big amplitude, loud volume. Frequency. So remember, frequency is kind of the number of waves per second. And that frequency and wavelength are kind of tied together. They're related to each other. When you change the frequency, you also change the wavelength. So this frequency affects pitch. And if you're not familiar with that word, that means like the highness or lowness of a note. Think of a violin as having a really high pitch and a bass as having a really low pitch. Okay, so when we stretch out the wave, and again, be really particular about how you draw these. I want a nice long wave here, and that means a low pitch, and that would be a low frequency. Okay, and a skinny wave here. So don't make it taller, just make it kind of shorter. Okay, sorry, don't make it taller, but make it skinnier. And that makes for a high pitch. So this would be like the sound that a bass makes, this wave, and this would be the sound that a violin makes, this wave. So waves are vibrations. Waves are vibrating things, and so when we vibrate certain things, there's kind of a natural frequency at which things tend to vibrate, a natural note that will cause something to vibrate. So in other words, you can kind of sing a note or play a note on an instrument, and you can cause other things to vibrate by doing that. And one of the things that comes from that is this idea of breaking a wine glass with your voice. And this is actually a real thing. So this is called resonance. And resonance is the ability of an object to vibrate by absorbing energy at its natural frequency. In other words, this is you hold a wine glass up in front of you, and if you sing just the right note, the wine glass kind of naturally vibrates at a certain speed, at a certain frequency. And so if you sing a note at just that right frequency, you can cause that wine glass to vibrate. And if you get it to vibrate enough, it can shatter. So take a look at this clip. This is a really cool clip from where you'll see this happening in really, really slow motion.
Shockwaves from a punch can do damage to the human body. Now we're going to time warp at 10,000 frames per second to see how sound waves destroy a glass. Jamie Vendera is famous for using the sound of his voice to destroy wine glasses. They seem to simply explode. But what's happening?
I know the sound waves broke the glass, but I couldn't see how. So I'm going to use our slow motion camera to see what we were missing. Instead of singing, I'm going to use a speaker and a tone generator. I have to find the natural vibrating frequency of the glass. I have to match this tone. That's it.
This is the exact tone to make this particular glass vibrate. When the tone is loud enough, the glass will shatter.
I can feel the glass shaking, but I can't see it. If I add a straw, then it's more obvious.
So what's happening here? The straw gets tossed side to side, but I can't see why.
Let's record it while I crank the volume. took 10,000 frames per second, and I took 1 second. If I were to play back this whole video, it would take 8 minutes to get through.
Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks.
Wow. So, as we would expect, the speaker breaks the glass nearest to it. And immediately we see a crack that goes all the way around the whole bottom of the frame. I'm going to play that back again. This is where the initial fracture happens, right nearby the speaker. And in about 3 frames, and this is 3 10,000ths of a second, we see this crack go along the bottom where the glass gets thicker and come right back up to the top where it's thin. So if we follow that a little more, this piece has just fallen off, but it doesn't in some sense even know that it's fallen off from the rest of the glass. All of the glass was shaking at about 300 hertz, 300 vibrations per second. And this piece is still doing that. You can see the corners of the glass still flexing as if they were influenced by the speaker, but the speaker is way too far away now to have that influence on this piece. It just has the leftover inertia. And we see that in all the pieces here, even along the top edge of this glass. This piece of glass is not resonant at that frequency anymore, so it can't get energy from the speaker, and all that we see shaking is the leftover energy from what the speaker gave it in order for it to break.
So, if you thought that glass couldn't bend, think again. Time warping changes the way we see the world because it makes the invisible visible.
All right. So here's a question for you. Which medium does sound travel the fastest in? And if you don't know what I mean by medium, well, you can maybe take a guess by the list of answers here. Gas, liquid, or solid. This is kind of the thing that the sound wave is traveling through. So does it travel the fastest through air, through water, or through solid objects like doors and things like that? Well, may be surprised about that. I know we're used to hearing sounds through air, but sound actually travels the best through solids. Now, here's why. Particles in a solid, one of the things that defines a solid as being a solid is the fact that its particles are very close together, and you can see that in this picture right here. Now, in a liquid, the particles have kind of heated up a little bit. We've talked about this idea of heating up and making particles move apart from each other. That's called thermal expansion. That's a word you should know. And in a liquid, in order to make something go from a solid to a liquid, we have to heat it up. So in a liquid, the atoms are a little bit further apart from each other, and in a gas, they are the furthest apart from each other. Now think about this. If you look at this little moving diagram here, remember that sound waves work by one particle bumping into another particle. And you can imagine that if the particles are farther apart from each other, then it's harder to get them to bump into each other. It's much easier to bump into, say, another person if it's really crowded. But if you're very spaced far apart, you don't really bump into people as much, right? So the same thing is true about air molecules. The further spaced apart they are, or molecules in general, the further spaced apart they are, the harder it is to get them to bump into each other. So sound actually travels best through a solid, which might be a little bit surprising to you, but I think that's just because we're used to hearing things through the gas of air. That something that I think is a little confusing about that is the idea that if you shut a door and somebody's on the other side of the door, it's harder to hear them. We'll talk about why that is in class. That has to do with the fact that some of the sound is sort of bouncing off of that door, but we'll kind of talk about that in class. So the speed at which sound travels, the speed of sound. The speed of sound is 300 meters per second in the air. It's about 1,500 meters per second in a liquid and about 2,500 meters per second in a dense solid. And so you can see that it actually travels much faster through a solid than it does through a gas. And as we said before, the medium is the stuff or the substance that a wave moves through. And sound needs to have a medium. This sound is atoms getting squished. It is waves of energy that are going through something, a solid or a liquid or a gas. It doesn't matter, but it has to be something. So, what's the medium here? Well, hopefully you said the medium is water here. That is what these waves are traveling through here, is water. That was a nice scribble. What's the medium here? Well, the medium is the people and other things. Anyway, the medium here would be the slinky. How about this? What is this? Well, check it out. This here, this thing, is the Earth. So what do we call waves moving through the Earth? Well, that's an earthquake, right? So in an earthquake, the medium would be, well, the Earth. All right, so I would like you to answer this question in your notes. This should be pretty easy at this point. Why is there no sound in outer space? Yeah, all those space movies with the sounds of laser beams and explosions and stuff like that. Yeah, they're lying to you. There's no sound in space. So I would like you to answer in your notes, why is there no sound in space? All right, sonar. This is something that you may have heard of before. Sonar is something that is used in submarines and boats and things like that. And sonar sends out an acoustic pulse and measures the distance in terms of the time for the echo of the pulse to return. All right, I'm going to say that one more time because that's kind of a long sentence. It sends out an acoustic pulse, meaning a sound, and measures the distance in terms of the time for the echo of the pulse to return. So you can kind of see this image here, and basically what's happening here is that pulse, that little sound wave, is going out from the boat, and it bumps into things and bounces off of things. And you know this is an echo. You've heard of this before. Just like if you're running in a race, it will take you longer to run a mile than it will take you to run, say, 50 yards. Okay, so the longer distance you have to go, the longer it takes. And so we can kind of measure that. We know how fast waves move through water, sound waves move through water, and so we can time how long it takes for the wave to hit something and bounce back, and then we can do some calculations to figure out how far away that object is. And that's how things like sonars on submarines work. That's how fish finders work and things like that. So that's what sonar is. So now bats and dolphins and whales and animals like that, they use sonar too, but we call it something else when it's an animal. There's a nice looking bat there. See, bats aren't so bad. They're kind of cute, sort of. So, can you guys please draw a picture of an animal using sonar in your notes and use the next slide as a guide? And I would like you guys to draw some waves, and make sure you draw something like a bat or a dolphin or something like that, and then you have to draw something that the waves are bouncing off of and show me the waves going out and bouncing off. Also, in animals, as I mentioned, it has a different name, which is echolocation. And that makes sense. They are locating things or finding things based on the echoes that they bounce off of them. So echolocation is a pretty good word for that. So what we're really talking about here, this idea of echoes and waves bouncing off of things and coming back, well, that's called reflection. And you kind of know that word already, right? Because you look at your reflection in the mirror, and when you look at your reflection in the mirror, that's just well, that's just light waves bouncing off of things, bouncing off of the mirror and coming back to you. So we call it that for all waves, any type of wave, whether it's a water wave like you see in this picture. You can see the waves kind of coming in and hitting this barrier and then kind of bouncing off. So if it's a water wave or a sound wave or a light wave, it doesn't matter. If it hits something and bounces off of it, we call it a reflection. And so that's kind of nice. You already know that word. Now, a word that you probably don't know is the word called diffraction. And this gets a little tricky because I know that reflection, diffraction, there's also another word that we'll learn about called refraction, but let's stick with this word diffraction now. They all kind of sound similar, but they're all a little bit different from each other. So you got to make sure that you understand the difference between these words. So diffraction is an interesting thing that sound waves do, and water waves, and pretty much any wave does this. It's just that it's most noticeable with sound waves. And this is the idea that, as you can kind of see in this picture, there's these waves that are kind of going through this opening here, but then you can see after they go through the opening, they kind of spread out. They go around the corner here like this, right? So I want you to draw this picture, and again, be really careful about how you draw this picture, okay? Make it look just like this picture. And so diffraction is this idea that waves bend around a barrier or when they go through an opening. And we'll talk about this in class, but think about this. You already know this happens because you can hear somebody when they're around a corner, like in a hallway or something like that. You can still hear them, so obviously the waves have to kind of go around that corner. So I really want you to get a sense of this and try to picture that every time there's a sound, there's these waves. So like if somebody says something, there's waves coming out of their mouth. And so if you're kind of in the school and you're standing in one hallway and they're kind of around the corner in another hallway, you can still hear them. So those waves must have gone around that corner and kind of curved around that corner to get to your ears. Okay, wave interference. This is a tricky topic. We'll talk about this a lot in class, but let me give you the basic idea right now. If you look within these little oval shapes here, these little circles here, where it says wave interaction, well, what you see is that there is sort of a little pattern that happens here, right? You can kind of see there and there and there and there. You can kind of see where these waves are creating this interesting little pattern here. Now, that's where two waves, the waves from this drop here and the waves from this drop here, are kind of overlapping each other. And you can see the same pattern in that nice little colorful animation up in the top right there. You can see how these waves, when they run into each other, they kind of have an effect on each other, okay? So let's take a look at this here. What we have is two different sound waves. We have the green wave and we have the blue wave. And what I want you to notice, and I'm just going to kind of let this play for a second here, and you really have to kind of look at this. So when they line up together, the green wave and the blue wave, you'll notice that it says constructive, right? And the black wave is basically the two waves added together. And you guys understand the idea of adding positive and negative numbers. So for example, 1 plus 1 equals 2. They add together, right? But 1 plus negative 1 equals 0. In other words, they kind of cancel each other out, right? 1 and negative 1 are kind of on the opposite sides of each other. And so if you add them together, they cancel each other out. Well, waves work in the same way. So right here at the constructive, you can see that the waves add together and make that black wave get basically twice as big. So right there, constructive. But when the waves are opposite each other, they basically destroy each other. You have one wave going on the sort of positive or the upside of that middle line, and one wave going on the negative or bottom side of that middle line. And so that's kind of like right there is kind of like we're adding 1 plus negative 1. So this is like 1 plus 1 equals 2, but right here we have up and that one was down, and so that's kind of like 1 plus -1 equals 0. And you can see right there, the black wave shows that they cancel each other out. Okay, now you know what it means to construct something, like constructing a building. You make it bigger, right? You build it up. And you know what destruction is. When you destroy something, you tear it down, you make it smaller. Okay, so same idea here. Constructive interference is when the waves add together, when they're both going the same way. Destructive interference is when they destroy each other, when they cancel each other out. So, interference. Constructive, we have two waves, this wave here, and this wave here. And when they come together, so these two waves, you can see from the arrows that they're headed towards each other. These waves are approaching each other. When they come together, basically we have, this is the small wave here, and this one is the big wave here. And you can see that those two waves add together to make the wave, basically the two waves added together. This would almost be like, say, adding maybe 2 plus 1 or something to get a total of 3. Okay, and then the waves kind of continue on their way over here and pass each other. Okay, so that would be constructive interference. Destructive interference, you can see that the waves are on opposite sides of each other. And if, like I said, I know this is kind of a confusing part here, but at the very least, if you can just remember that if the waves are on the same side of the rope or the slinky or whatever, if they're on the same side, they will add together. If they are on opposite sides, they will cancel each other out. Okay, and you can see here's one wave that was on the top, here's the one wave that was on the bottom, and when they come together, they cancel each other out, and the rope basically doesn't move at all. That's no wave at all, right? And then they pass by each other over here. All right, so we have learned all about sound, and we know now that sound is vibrations. We learned about wave properties in sound, and remember, this part is really important. We have to remember that we have wave properties, which are amplitude, frequency, wavelength, things like that. And we need to understand that those properties, changing those properties, will change the sound in a certain way. So when we change the amplitude of a wave, that affects the volume. And when we change the frequency of a wave, that affects the pitch. We learned that resonance is causing an object to vibrate at its natural frequency, like making a wine glass break with your voice. By the way, don't try that at home. That's kind of dangerous. We learned that the medium is the stuff that the sound travels through, solids, liquids, and gases. And we learned about sonar and echolocation, and that's basically bouncing sound off of things to figure out where they are. We learned about reflection, which is the idea of bouncing sound off of something. That's what an echo is. We learned about diffraction, which is sound bending when it goes around a corner or through an opening like a door. We learned about wave interference. Constructive means they're on the same side and they add together. Destructive means they're on opposite sides and they cancel each other out. Don't forget to tell me where the owl is and do your summary, and I will see you in class.